Hello, this video explains how and why we are compensating for clock drift of SonarPoint recorders when we are using the recordings from multiple recorders combined into a single multi-channel sound file to localize sound sources. So let's take a look at this simple graphic here, which is really for a different system, but we'll make it work here. And let's say these 4 tripods are 4 recorders on the seafloor. And let's say this is some sort of a vocalizing target, maybe a whale, that we're trying to localize. Where does its sound coming from? And as we can see, assuming all recorders have the exact same time, their clocks are perfectly synchronized, then in the recording file we can expect to see a sound from the whale at this recorder first, simply because it's closest, and then probably at this recorder, and finally at these two here. Whichever one, maybe this one is furthest away, will receive the sound latest. But the problem is that the clocks on our recorders are probably not going to stay synchronized. SonarPoint recorders have very, very precise clocks that are GPS calibrated and synchronized before deployment. And that gives them a very small drift that we observed at around 50 parts per billion, which translated to signal runtime and range measurement errors is equivalent of about a 6-meter accumulated ranging error per 24 hours of operation, or also 25 centimeter per hour of operation. But it adds up if your recorders here are now sitting on the seafloor for maybe several weeks. So how do we deal with that? Well, we attach a synchronization pinger to one of the mooring strings, and I will show that here. Here you see 4 mooring strings, 4 acoustic releases here, sacrificial weights. Here the 4 SonarPoint recorders, and then this guy here, and let's look a little bit closer, is the synchronization pinger. So it's just co-located with a recorder on one of the mooring strings in the array. Now, I want to point out here that this video is really about the theory of how this all works and how you can manually do clock drift compensation until we have updated our file merging utility, which is called wave merge, to also do this compensation based on the synchronization pinger automatically. For now, we'll do it with a spreadsheet, and you'll see how this is done. Now, we need to visualize a little bit how this works. Let's say you have all the recorders, their clocks were GPS synchronized before deployment, as was the synchronization pinger, and you throw them into the water, and the pinger pings at the top of a GPS second. Everything is perfectly aligned. There wasn't enough time for any clock drift to occur. What would we expect to see? Well, we would expect to see that the ping from the synchronization pinger, which by the way happens once per recording interval, and specifically 30 seconds after the beginning of the recording interval. So if you have 10-minute recording intervals, there's one ping every 10 minutes. It would be seen by this recorder where it's co-located first, right? 30 seconds after beginning of the interval, this guy pings, and here this recorder receives it almost right away because it's closest. This one will receive the signal somewhat later because it's further away. We have to account for the signal runtime at a speed of 1500 meters per second approximately, and these ones later and later. How can we use this to compensate for drift of these various clocks? And remember, any one of the recorder clocks will drift in different ways, and so will the clock of the synchronization pinger itself. Well, let's just take an example here. Let's say just after you threw your recorders in the water, you deployed them, and then sometime later you recovered them, and you look at the file, and you find that this recorder here receives the signal at first 100 milliseconds after the beginning of a second, which means it's about 150-meter distance from the synchronization pinger. A day later, rather than receiving it 100 milliseconds after the beginning of the second, maybe now it's, whatever, 101 millisecond. How could that be explained? Well, that could be explained by this clock of this recorder being a bit fast, having accumulated a 1 millisecond error. It could also be explained by the pinger having pinged a little bit later, so its clock has drifted. They are both possibilities. But what we can say is that the combined clock error of the synchronization pinger and of this recorder amounts to 1 millisecond, as long as this recorder hasn't somehow moved. Of course, if it had moved 1.5 meters away, then we would have also seen a 1 millisecond error and so on, So what we can do now is we could simply say, well, all right, I look at my very first recording file after deployment, and these define at what time I should see the ping. And if I see in some other recording file the ping from the synchronization ping some amount of time later, say 10 milliseconds later now, then I simply need to subtract 10 milliseconds from my time measurements. And we do that for all of these recorders. And now, even for this one, and now they are effectively synchronized and stay in synchronization with each other because they are synchronized now to the synchronization pinger. Now, unfortunately, one problem we have is that the method that I just explained depends on synchronizing the recorders, GPS synchronizing it and calibrating it a short period of time before you put them in the water, so that the amount of clock drift that is to be expected until you have the opportunity to do this measurement of establishing the expected ping arrival times from the synchronization pinger when there's no clock drift. It's a short window of opportunity, right? Every hour of time elapsed since you GPS calibrated your array is 25 centimeter of error. And sometimes, though, you'll be operating on the boat, you want to maybe switch on your recorders and get them GPS calibrated well in advance so you don't have to worry about that anymore. It can be a little bit chaotic. How can we get around that problem? And the solution is that after you recover the recorders, you can put them all in a bucket. And then you will probably have this thing called the pinger pole on your boat because you're going to use that for a separate task, which is the acoustic survey of the location of the recorders on the seafloor. And you put this transducer into the bucket here, along with all the recorders. And this sonar transducer will ping once per second. It actually pings at the top of each GPS second, once per second. When you now look at the recording files of the 4 recorders, if their clocks were still perfectly synchronized to GPS, then they would all receive the ping at the very same time, exactly at the top of the second, really 10 milliseconds after the top of the second is how this system works, But to the extent that they're all receiving it at different times, you now know how far these clocks have drifted off from each other, and you can compensate for that. And then you can use this end of recording as your reference, and from there establish, based on the time of reception of the sync pings at each recorder, in a given file of interest that you're now analyzing, what time shift, what compensation is needed for that particular recording file. And so we'll do that next. So I now have here a number of merged files from a deployment in Morro Bay. This is a date code 2021, July 21st at 1930 hours, for example. For this file, they're all 4-channel files because there were 4 recorders in the water. So they've already gone through wave merge, but without clock drift compensation. And this one here is my resynchronization file, the bucket synchronization, where we just saw the picture. Let's take a look at that in Audacity here. Okay, that's coming up. And notice this stuff here. These, we are now looking at time domain. These are the individual pings of the ping up hole transducer once I put it into the bucket, and here all the 4 recorders are listening to it. These are the 4 channels. Let's just zoom in on just a couple of these pings. Okay, and here you can see that these pingers are, the 4 recorders are receiving the pings at a slightly different time, even though they are very close to each other in the bucket. So this is the manifestation of the clock drift after, in this case, about 10 days, 11 days of operation, I believe. So let's take a look, zoom in a little bit more, see how much drift we accumulated there. View, zoom, zoom to selection, and what's our biggest error here between earliest and latest apparent detection. It's about 58 milliseconds in 10 days. Is about 5.8, well, 5 millisecond in 11 days or so. 5 milliseconds per day in 11 days is 7.5 meters per day. That's close to what the typical expected value is. So one compensation we now can do is we can adjust these to all come together in the same point, you know, like adjust this one relative to this one. Actually, what we're really doing is we're adjusting it relative to the top of the second, each one of them. So that's the first compensation that we can do. So the second part of the compensation is we now need to establish at what time the each recorder should see the synchronization ping from the synchronization pinger. At what time that should be. Remember, the further it's away from the synchronization pinger, the later. And we do that now at the end of the deployment, which for us was August 1st at 1440 hours, which is 2 hours before we got around to doing the pinger pole. The clock resynchronization using the pinger pole. So just a 2 hour or a 50 centimeter expected error in there. And we look at what time we should receive these pings now, or we are receiving the pings now, and then in any particular recording file of interest, maybe 5 days earlier, 10 days earlier, whatever, if we receive the sync pings at a somewhat different time, then we know that that's the clock drift that we also need to compensate for that particular file. So Let's see if we can find it here. The sync ping should be at about 30 seconds. Is co-located with this first channel up here, so I bet you this is the sync ping. Okay. This might be the sync ping here. You might go, well, are these also the sync pings? How can I be sure here? Just looks like a bunch of noise. Well, we can just go to the spectrogram display and see if it's at the right frequency. Zoom to fit. And here we have something at 34 kilohertz. That's certainly our sync ping because the sync ping is at 34 kilohertz. How about the next one here? Spectrogram. Yep, it's this one up here. We can see that here. I'll do this on the other two channels as well. Again, it's apparent. And here as well. Let me zoom in on this. Okay. So here and here and here, notice there's echoes of our sync ping visible as well, but we're going to go for the first one. Now it's kind of hard to be very precise in the spectrum display because it averages a bunch of samples. So I like to go to this, way more crisp. Note this one is here. See what ping we have to look for. It's this guy here, right? Same here. It's the first one, and here. Alright, and now I can do these measurements. This one was received at 29.92. I actually want to be more precise than that. You know, 21.920 something. I want to be even more precise than that. Okay, here, 29.9203. Here's 9205, so it's 9203. So I want to get to 4 digits after the decimal point, so within 100 microseconds, and I can do that for all of them now, and I can do it for different files. All right, so in the final step of this, let's look at the spreadsheet that does the clock compensation here and how it's used. So yellow fields are stuff where you enter data, and then blue fields are computed values. Here we have the 4 recorders, serial number 1010, which had the sync pinger co-located 2006, 2020, and 2021. And then the first step, and what we need to enter, is the resync pinger pole time of arrival. So this is just a fractional seconds. We are just arbitrarily selecting the 0 point S of GPS time when as our reference for adjustment here. So this particular pinger received the ping from the pinger pole at apparently always 0.111 seconds before the top of a second, and this one 0.238 after the beginning of a second, and so on and so forth. And therefore the compensation that we use is just this value sign inverted. It came in at, the ping was received at minus 0.0111 seconds. Therefore, we have to add compensation value of 0.0111 seconds to any measurement with this file, and same for the other ones. Then we look at what time we received the synchronization ping in the final recording file. So it's important that that is not too far separated in time from when we did the resync, the bucket test here. We see it's a 2-hour difference in time, so 50 centimeter expected error on account of this time elapsed. And here we received it for this channel at 29.9203 seconds from the start of a recording file. Here it's at 30.1281 seconds, and so on and so forth. Then for our target file, the one that we now want to do some localization with, here I selected one for July 25th, so about a week before the end of the recording. And at that time we received the sync pinger signal at 29.9759 seconds, up from 29.9203 seconds, and that is a compensation value of minus 0.0556 seconds for this channel in this particular recording file, this recording file of July 25th at 1930. And adding these two compensations up gives us our total compensation that we need to apply to each channel. And notice how they are different compensation value for each channel. Let's go to just flip back and forth to a different file. 21st of June, this is just after deployment. And notice the G column here. You'll see the compensation values change. So they change over time. So each 10-minute file you apply a different compensation value for. Now, I know this is kind of confusing, to say the least. My recommendation is just use this spreadsheet for now. You know, the signal picking for the synchronization ping is relatively easy. All you have to do is, you know, enter these three values here, and then things are computed for you. Take these numbers and apply that, add that number to any time measurements, you know, that you have. If you're measuring a certain event at time 3 minutes exactly in your recording file, then you really should add this amount of time. So your real detection time was 79.6 milliseconds before 3 minutes from the start of the file, and the same for the other channels, and that will give you the synchronization that you need to subsequently localize these sounds. In the future, the wave merge utility will do that all automatically for you. You don't have to do this, so there'll be a zero time investment. Although there'll be a little review, you'll have a little graph that you look at to make sure that the software correctly picked the synchronization pings as it should. And that's it. Thank you very much.